Welcome back. Today we're going to look at section 7.1a. We're studying properties of exponential functions. So our learning target today is to graph an exponential equation, just a basic y equals a times b to the x. And then to determine growth or decay and identify the Y-intercept, domain, range, and asymptote. And then tomorrow we'll start looking at transformations of these. So today we're just studying the basic function. To graph an exponential function of this form, y equals a times b to the x power, the first thing we want to do is make a table of values. And then we'll plot those points and connect them. And we should see the same type or the same shape graph in all of these. All right, so we're going to graph the first one here, y equals just 2 to the x power. So we've started a table of values here. And we're actually going to start with the bottom. What is 2 to the third power? Okay, that's what the equation is giving us. We're putting our x in as our power. So 2 to the third power gets us an 8. Let's work our way up here. 2 squared would get us a 4. 2 to the first power would be just 2. And remember, anything to the 0 power gets you a 1. It's one of our exponent rules. And then also remember, with negative exponents, we have to flip it. So 2 to the negative 1 is actually going to be 1 over 2, 1/2. 2 to the negative 2 is going to be 1 over 2 squared, which would be 1/4. And then 2 to the negative 3 is going to be 1 over 2 cubed. And we already found out 2 cubed was 8, so this would be 1/8. And hopefully you can notice that as we move from the bottom of our chart to the top, we are cutting everything in half. Everything's half as big. As we move from the top down, everything gets doubled. So 1/8 turns into 1/4, 1/2, a full 1, then 2, 4, and 8. All right, so we're going to take a minute here and plot these points. We are looking at -3 and 1/8. Now, 1/8 is going to be a little hard to graph on this tiny grid, and my board is off just a little bit here. But do the best you can. It should be just above that x-axis. At -2, we're at 1/4. So just slightly higher than what we were before. And then at -1, we are at 1/2. And at 0, we are up at 1. And then 1, 2, 2, 4, and 3, 8. So you can kind of see that it is curving up to the right. And as our numbers get further, for x get smaller and smaller. So if we had continued this chart, say used a -4, -5, we're going to keep cutting those numbers in half for our y. So we'd be at 1/16, 1/32. They're just getting smaller and smaller and smaller. But they're just always going to be slightly above that x-axis. So our graph, if we connect these dots, is actually going to be right above the x-axis and then curving up to the right. Okay. Let's look at our y-intercept. Remember, the y-intercept is the value for y when x is 0. And if you look at our table here, we found that to be 1. The asymptote, we have a little definition for that right down here at the bottom. An asymptote is a line that our graph approaches as x or y goes towards infinity. For exponential equations, this is just going to be a horizontal line, y equals some number. Okay, so where is it leveling off? Where does my graph approach a horizontal line? And you should see that it's getting closer and closer and closer here to this x-axis. So my asymptote is actually the x-axis, which has the equation y equals 0. My domain, there's no value that I can't plug in for x, so my domain is going to be all reals. But my range, I do have this cutoff. Now, my points get close to that green line, but they're never actually going to touch it. So my y values are never actually going to get to 0. They're always going to be just slightly above that. So our y limit here would be everything has to be above the 0 mark. And this is considered exponential growth. As we move to the right, my numbers are getting larger and larger. So as I move this way, my y values are getting higher. My graph is growing. We call this exponential growth. All right, let's look at this next one. We have y equals 1/3 to the x power. Again, we're going to start with the positive exponents here at the bottom. And we have 1/3 being raised to a third power. We're cubing it. So if we cube the 1, we get 1. And if you cube the 3, you get 27. Moving up, 1/3 squared. We square both the 1 and the 3, and we get 1/9. 1/3 to the first power is just 1/3. Anything to the 0 power, remember, is just a 1. And then with our negative exponents, remember, we have to flip it. So 1/3 to a -1 is actually going to flip and become a 3. 1/3 to a -2 is going to flip and get squared and become a 9. And then 1/3 to a -3 power is going to flip over and become a 3, get cubed, and be a 27. Okay? So let's look at plotting some of these points. When x is -3, we are way up at 27, which is off my graph, and I'm going to have enough other points that I don't actually have to use that one. At -2 for x, I am up here at 9. At -1, I'm up at 3. At 0, I'm at 1. 1, I'm at 1/3. And then I'm at 1/9, and then 1/27. And again, my graph is off a little bit here. We're going to do the best we can. What we should be seeing is that we are approaching that x-axis now, coming down from the high up on the left side, curving down and leveling off just above that x-axis. Okay? This is considered an exponential decay curve because my points are actually going down. They're getting smaller as x gets bigger. So as my x coordinates gets bigger, you can see that my y values are actually getting smaller. Once again, our y-intercept is the value for y when x is 0. Again, it's a 0, 1. The asymptote is the same as we had before. All of my dots are approaching that x-axis. So y equals 0. My domain is all real numbers. There's nothing I can't put in for x. But again, my range, all my y values are going to be above that x-axis. So y is greater than 0. Not greater than or equal to, strictly greater than. Okay, a couple things that I want you to notice from these two equations. In both cases, we had a y-intercept of 1. In both cases, we had an asymptote at y equals 0. In both cases, our domain was all reals and our range was greater than 0. The shape of our graphs was a little different. One was increasing or growing, and the other was decaying. It was going down or decreasing as we moved to the right. I also want you to notice a pattern in the chart here, in our table. Notice that when x was 3, we had 1/27th, and when x was -3, we had just 27. Those are reciprocals, right? When x was 2, we had 1/9. When we had -2, we had a 9. So again, they're just reciprocals. So if you know half of your table, you should be able to flip them over and get the other half. Same thing happened here. We had a 3 getting us an 8, and a -3 getting us a 1/8. Okay? And again, those two were similar. We had a 4 and a 1/4. We have a 1/2 and a 2. So there's all of these reciprocal values in our table. All right. So kind of to summarize what we've talked about. We have this exponential function, y equals a times b to the x power. Some requirements: a cannot equal 0 because timesing something by 0 is going to make everything 0. Our b value has to be greater than 0, but it can't be 1 because if we put a 1 in and raise it to a power, nothing happens. We're just going to have a 1. The b in this case, the a and b are going to be constants, and it's the x that's our independent variable. Okay? So what made it an exponential growth situation was that our b value was something bigger than a 1. Like in this case, we had a 2. What makes it decay is when our b value was something between 0 and 1. I think the previous example we did, we had a 1/3. Here we have a 1/2. If the base that's being raised to the power is something between 0 and 1, it's going to decay. If that base is bigger than 1, it's going to grow. We talked about the y-intercept is the same for both of them at 0, 1. We talked about having this asymptote, in this case at the x-axis was our asymptote, y = 0. And our y-intercept, in the two pictures we have on this page, notice that our a value was a 1. There was nothing extra in front. So when we had that equation, a times b to the x, this one is just y = 1 times 2 to the x, or y = 1 times 1/2 to the x. Our a value is just a 1, and that was our y-intercept. So if we put a different number in there for a, our y-intercept is going to change as well. Domain is always going to be all reals, and our range is going to be y is greater than 0 until we start transforming them tomorrow. Okay, so let's practice identifying some key features of exponential equations without having to graph it first. In this equation, the y-intercept is always going to be 0a, and there are two types of exponential equations. We have our growth and we have our decay. Okay? So that's going to be our y-intercept, or our starting point. And then the growth and decay is going to be based on the base that's being raised to that power. One thing to watch out for, you might want to highlight this. If the exponent is a negative number, remember we have to flip our fraction. So make sure you flip that before you decide if it's decay or growth. Okay? And then the percent growth or decay is really just how much above or below 1, what's the difference between our base and a 1 converted into a percent. Okay, so let's try these three. Remember we have y = a times b to the x. Okay? So we look at our base. In this case, our base is 1.3. Since 1.3 is something bigger than 1, this is going to grow. Okay? Our y-intercept is going to be our a value. It's always 0, excuse me, 0, a. In this case, our a value is that 2. Okay? And now the percent, how much does it grow or decay? Since we are looking at a 1.3, that if we take away the initial 1, a regular 100% of the initial amount, we end up with a 0.3. That means we are 0.3 or 30%, since 0.3 represents 30%. We're 30% more than just a regular 1. So we have a 30% growth. Okay, looking at our next example. We look at our base, the piece that's being raised to the exponent. We have a 0.65. Since that base is between 0 and 1, it's going to decay. Our y-intercept comes from this front number. So we have 0, 1/2, or 0.5. And then to figure out our percent growth or decay, 0.65 is 65%, right? How much is that compared to 100%? Are we lower or we're higher? In this case, we're higher. How much do we have to raise it to get to 100%? Well, let's look at 1 minus 0.65, or 100% minus 65%. we are off by 35%. So we are looking at a 35% decay. Percent decay is 35. You're basically looking at how much do you have to change to get to a 1. Okay? Here we went up 30%. We were 30% higher than a 1. Here we are 35% lower than a 1. So it's decaying. Okay? Our last example here. Notice that we have this negative exponent. And that's going to cause the base, this 5 here, to have to flip. Okay? So we really want to look at this as y equals 6 times 1/5 to the x power. By flipping the 5, we now can make that exponent just a regular x. So because it's a 1/5, it is going to decay. That's a number between 0 and 1. So it's going to get small. My totals are going to get smaller as x gets bigger. My y-intercept comes from that front number, that's 6. And now to figure out the percent of growth or decay, think of 1/5. 1/5 is the same as 2/10 or 0.2. So right now there's a 20% piece in there. That means we're 80% away from being a whole. Okay? 1 minus 1/5 would give us 4/5 or 0.8. We're 80% away. So we have an 80% decay. This was a decay as well. Okay? All right, so you guys are going to be doing some graphing, just basic ones. We're not going to transform them at all. So again, we're going to make a table of values and plot those points. For your table, I want your x's to go from -3 to +3. And then you're going to have some questions where you are just identifying whether it's growth, decay, the y-intercept, kind of getting ready to do more graphing tomorrow. Okay? You guys are going to work on worksheet 7.1a. Let me know if you have any questions.